Here are the 9 characteristics of Fedora modules: domain specificity, mandatory operation, limited central accessibility, fast processing, informational encapsulation, shallow outputs, fixed neural architecture, characteristic and specific breakdown patterns, and characteristic ontogenetic pace and sequencing. Notice that I'm marking 3 of these in bold, because they are the ones that figure most prominently in Fedora's own discussion and in the modularity literature in general. So let's review each of those 3 in turn. Whether a system, let's begin with domain specific. Right? So whether a system is domain specific or not depends on the range of questions to which it computes answers. Depending on how broad or narrow that range is, the system will be classified as domain general or domain specific. Modules typically operate on a very specific domain. So they're only sensitive to certain kinds of stimuli, contents, or information. For instance, within the visual system, there may be a submodule that only detects certain shapes while ignoring all other aspects of a figure, while another one may be wholly devoted to the orientation of lines. The speech system springs into action whenever it encounters linguistic utterances, but not when it meets other kinds of sounds, such as, say, instrumental music. Furthermore, even when you're hearing a composite stimulus, such as someone singing a song, the linguistic system will only engage with the linguistic aspects of the stimulus, not the musical ones. So this diagram represents domain specificity. Out of all the kinds of stimuli and information that impinge on an organism, a module will only deal with a specific subset. This, by the way, is one of the main features that gives Fedora's proposal its flavor. And this is what differentiates a vertical view on the mind's organization from a horizontal one. It's not that you have learning mechanisms that indifferently accept all kinds of data. Rather, you have systems whose principles of operation are specially tailored and sensitive to different kinds of information. Then you have limited central accessibility and informational encapsulation. I'm treating this as two sides of the same coin, right? Because they are both manifestations of restrictions in the flow of information to the module and out of the module. For instance, limited central access refers to the assumption that the central system only has access to the module's output, and it's not privy to the information processing that goes on inside the module. In particular, it has no access to the database and algorithms employed by the module. So in short, the modules are completely opaque to the central system. So, for example, if we follow Mar's theory, then in your visual module, in your early vision module, there is a procedure for finding edges. This process relies on finding zero crossings. A zero crossing is a point where the sign of a function changes, and that it goes from positive to negative or vice versa, so that it crosses the horizontal axis at 0, hence the name. The function that is used for this search may be a second-order derivative expression computed from the image. So, if this is true, your module is able to calculate derivatives or something computationally equivalent. However, this process is hermetically tucked away inside your module. Your central systems can't pry the module open and extract that information to help you in your calculus exam, for instance, even if you are desperately in need of help. So, in short, limited central accessibility means that external systems, that is, central systems and other modules, have restricted access to what goes on inside the module. The central system cannot help itself to the information handled in their intermediate processes within the modules, but only to their outcomes. They cannot read or write any contents inside the module. So modules are perfect black boxes as far as the central system is concerned. This characteristic has gone under other names in the literature, such as cognitive impenetrability, that's the name given to it by Zenon Pilishin, and informational opacity. The other side of the coin is called informational encapsulation, and it refers to the fact that modules can only access their proprietary database, so to speak. So informational encapsulation entails that the processes inside the module cannot access information residing outside the module. In general, they cannot access the information from higher-level systems or from other modules. So, not only is the case that the central system and other modules cannot have access to a module, but also that the module can't help itself to the information housed in central systems either. Fodor was fond of illustrating the opacity and encapsulation of modules with the Müller-Lyer figure, shown here. So let me ask you, which line seems longer? If you're like me, you will say that the top line seems longer. Now, if we measure the lines, we'll see that they are exactly the same length, despite appearances. So now we know that the lines are of the same length. Our central system has acquired the belief that the two lines are of the same length. Okay, now let me ask you the question again. Which line seems longer? Again, emphasis on seems. The answer is the same as in the beginning. The top line seems longer. And this in spite of the fact that you actually know that they are of the same length. Fodor interprets this as showing that your central system, where your beliefs are housed, can't influence your early visual system, even in a situation like this where your beliefs are obviously relevant to what you're seeing. And the reason your central beliefs can't influence early vision is that early vision is, in Fodor's view, modular, and so its processing can't be influenced by a central system. So, given informational encapsulation and opacity, seeing isn't believing.